video is about factoring quadratic expressions. The word factoring means to write as a product. So we can factor things like the number 72, for example, by writing it as a product of 8 and 9, right? A product means a multiplication problem. If you wanted to fully factor the number 72, it would mean to break each of those factors down into their products also. So 72 equals, I can break 8 into 4 times 2, for example. I can break 9 into 3 times 3. I can go even one step further by breaking that 4 into 2 times 2. Now I've fully factored the number 72. So breaking each of the factors down into their lowest factors as well. So factoring means to write as a product. One type of factoring is to factor out the greatest common monomial, which just means if you look at the terms in the expression, for example, 4x minus 10, you're going to look for the number that you can divide both of those terms by, and then take it out as if you're undistributing it. So I notice that I can divide 4x by 2, and I can also divide the minus 10 by 2. And so I'm going to factor out that 2. The 2 here is the greatest common monomial factor. That's what this means. So I'm going to take out the 2. I need to show the 2 in front of the parentheses, as if I am undistributing it, and then divide each term by that 2. So 4x, when I divide it by 2, leaves me with 2x, and the minus 10, when I divide it by 2, leaves me with minus 5. Now you can always check if your factoring is correct by redistributing the 2 back in, and sure enough we would get 4x minus 10. So we've taken the expression, 4x minus 10, and written it as a product. We've written it as a multiplication problem. And it's fully factored because I can't do anything else with the 2x minus 5. Let's take the next example. Now I have a 6, a negative 18, and a 9. And I know I can divide those all by 3. But I also have x's in common. Now the first term has x to the third, the middle term has x squared, and the last term has x. The most I can take out is just a single x because the final term only has one x to give away. So I'm going to take out the 3x. That is the greatest common monomial factor here. And make sure you show the 3x in front of the parentheses. And now we divide each term. So 6x to the third, when I divide it by 3x, leaves me with 2x squared, right? Because I've taken out one of the x's. Then I'm going to divide my negative 18 by 3x, and I get minus 6, a single x left in the middle term. And the last term is 9x divided by 3x is just going to give me a 3. No x's left on that term, close the parentheses. I have written it as a product, and there's nothing else I can do to break it down any further. The final terms here, I have negative 12 and 48. So I know I can divide them both by negative 12. Now, if the first term is negative, if the first term of your expression is negative, please make sure that you're taking out the negative. The negative has to come outside of the parentheses in order for it to be fully factored. So I can definitely divide by that negative 12. The most x's I can take out is 1, because this only has a single x. So I'm going to take out an x. And the most y's that I can take out is 3. There's my greatest common monomial factor, and then I'm going to start my parentheses and say, what's left? So divide my first term. Now, this whole thing here is the first term. I'm going to divide that whole thing by negative 12x, y to the third, and what will be left is simply a 1. There will be an x left, and all of the y's have been taken out. So there's really just an x here in the first spot. And then I'm going to take this term and divide it. When I divide that by negative 12, I get minus 4. The x has been taken out, and there's a single y left over. Now that's fully factored as well. This is another type of factoring. These are quadratic trinomials. Trinomial is a word that means 3 terms. If you've learned quadratic functions, you'll know that these all look like they're in standard form. Ax squared plus bx plus c. Those are called quadratic trinomials. And so we're going to factor these into the product of 2 binomials. A binomial means 2 terms. It's as if you've FOILed something or multiplied 2 of these binomials together, and you're trying to figure out what were the 2 binomials that were multiplied to make this final trinomial. So when I take that x squared and I break it up into the parentheses, I know that each parentheses is going to start with a single x. That's because x times x gets me that x squared. Then I'm going to skip to this number, positive 20, because I know that the other two numbers in these parentheses, when I multiply them together, are going to have to equal that 20. So I'm thinking of the factors of 20. They include 2 and 10, 1 and 20, 4 and 5, and also the negative 1 and negative 20, negative 2, negative 10, and negative 4 and negative 5, because those would also make positive 20. How do I decide which pair of constants to put into the parentheses? That's when I look at the middle term. When I add the two numbers together, they must equal b, the coefficient there. They have to equal negative 9 when I add them together. So I can see that 1 and 20 is never going to add up to negative 9. 2 and 10 is never going to add up to negative 9. 4 and 5, however, will add up to negative 9 if they're both negative. So I'm going to fill in the negative 4 and the negative 5. Look at my two binomials that I got as my answer, x minus 4, x minus 5. Imagine multiplying those two things together and see if it gets you what you started with. If you do the math correctly, you'll see it's going to be x squared minus 9x plus 20. And therefore this is the factored form of that trinomial. Let's try that again. So we have trinomial. It's going to get factored into two binomials. I start by filling in an x in each parentheses. Then I look to my negative 12. The factors of negative 12 include 3 and 4. One of them would have to be negative, but not both this time. 2 and 6. Again, one of them would have to be negative, but not both. 1 and 12. Again, one of them would have to be negative, but not both. And that's all of them. So I'm looking for the pair that's going to add up to positive 3. I know 1 and negative 12 is not going to work. Negative 3 and 4, 3 and negative 4, 2 and negative 6. In fact, none of these are going to work. When that happens, if you've really exhausted all of the factors of that negative 12, none of them add up to the middle term. It means the trinomial is not factorable, and that happens more often than you would think. So if you've really gone through every option and none of them work, you're not going to be able to factor it, and you can write not factorable. But you really need to check every option. Don't just give up after you've checked a few and decide that it's not factorable. And then this final example, I put an extra little step in here. I noticed the first thing right away is that all three of those numbers are divisible by 2. And so it kind of reminds me of the first slide, where I want to take out the common factor first. If there is a common factor, it's always a good idea to take that out first, then see if there's anything else you can do. So I'm taking out the 2. What's left is x squared, 9x, and 8. Now I'm not done this time, because what I have in the parentheses here can get broken down even further. This is like on the first slide when I did a 72, and I broke it into 8 and 9, but then I had to keep going by breaking down the 8 and breaking down the 9. So here, the entire expression in parentheses is going to get split into two binomials. Remember to keep the 2 out front that was there from the beginning. I'm going to split the x squared into x and x, and then look to this 8. What multiplies to make 8 is 8 and 1 and 2 and 4. And I see right off the bat, positive 8 and positive 1 is going to work, because that adds up to our middle term, which is 9, right? This middle term here. So I'm going to add my positive 1 and my positive 8. And I can always check my answer by multiplying all of this back together to make sure that I get the original expression that I started with. Here's a third type of factoring. These are called perfect square trinomials. Now they look a lot like the trinomials from the previous slide. You'll only see a difference here after you try to start factoring it. So we're going to set up our parentheses. We're going to fill in our x and our x. Then we're going to look to that 25. Things that make 25 are 5 times 5 and 1 times 25. And remember that we're trying to add up to the middle term, which is a negative 10. Well, 5 and 5 is going to add up to that, as long as they're both negative 5s. And negative 5s will work, because a negative times a negative is positive 25. So I can fill in a negative 5 and a negative 5. When I see that I have the same binomial factor written twice, you can just go one extra step further and simplify your final answer to this. X minus 5 quantity squared, right? Because that means the same exact thing. So if you ever get the same factor twice, I would rather you write it with a square. Those are called perfect square trinomials. Breaking up this one with x and x. What multiplies to make 9 that adds up to 6? Should be clear that it's positive 3 and positive 3. And so we write our final answer as x plus 3 quantity squared. And the fourth type of factoring in this video, factoring the difference of squares. All right, this one is drastically different from the trinomial because they're not even trinomials to begin with. It's just x squared minus 49. So you'll notice that the term that is missing is the one that has just an x attached to it. So if you want to imagine it, this is the same as saying x squared plus 0x minus 49. I don't usually go through the process of writing that out, but it's sometimes helpful to imagine it that way when you're trying to factor it, because it's not that different from what we just did on the previous slide if you look at it written as a trinomial. What you would be doing is breaking up the x squared and trying to say what multiplies to make negative 49 that adds up to 0 in my middle term. The product that I think of for 49 is going to be a 7 times a negative 7. Because 7 and negative 7 are opposites of each other, they will add up to 0x in the middle. And so I can fill in my positive 7 and my negative 7, and that's the factored version of this. Now you can skip that middle step where you fill in the 0x if you recognize that you have a difference of perfect squares. Remember, difference means a subtraction problem. Perfect squares are things like 9, 16, 25, right? 3 times 3, 4 times 4, 5 times 5. Even x squared, because it's x times x. So in this problem, I had a perfect square right here, I had a perfect square right here, and I had a subtraction problem. So that made it a difference of squares. If you recognize it right away, you can skip to this last step where you fill in x plus 7, x minus 7. So in this next example, I recognize that I have perfect squares. This is a perfect square. This is a perfect square. It's a subtraction problem in between. So I can skip to my final step and break it up. I've got 4x squared. The square root of that would be 2x, because 2x times 2x is 4x squared. I have 81. I know the square root of 81 is 9. In order to get a negative out of it, I know one of them is going to have to be plus 9 and one of them is going to have to be minus 9. This is not the same thing twice, so I'm done. I can leave my final answer just like this. And that is all.